Hello and welcome students to the next lecture of the hypothesis testing. In the last lecture we had seen the numericals based on the t-test, and today's lecture we will begin with the chi-square test. So the chi-square distribution, it is a measure of actual divergence of the observed and the expected frequencies. So whenever in a data we have some observed frequencies and some expected frequencies, so this chi-square will give the actual divergence of the two measures. Here the formula for the chi-square has been defined as chi-square. So this is the symbol for the chi-square. Chi-square is equal to sigma within the bracket FO, which is the observed frequency, minus of FE, which is the expected frequency. So this is the square difference of observed frequencies minus expected frequencies in the square divided by the expected frequency. So this will give the exact difference between the observed and the expected frequencies. It basically gives the idea of the goodness of the fit, whether the data can be how good can be fit to some distribution or not. Let's understand another definition, that is of the degree of freedom, which will be used in the chi-square formula. The degree of freedom refers to the number of independent constraints in a set of data. Independent constraints can be considered as the sets or the values or the parameters or the properties. So these will give you the degree of freedom. Now, so you will be using this formula for calculation of the degree of freedom, r minus 1 multiplied by c minus 1, where r is the number of rows and c is the number of columns. So basically these are the different classification criterias. Goodness of fit. Let's talk about the goodness of it. The value of chi-square is used to find the divergence of the observed frequency from the expected frequency. Now this is important. If the value of p probability is high, if the value of p is high, then the fit is said to be good. That means there is no significance difference. So no significant difference between the observed and the expected value. That is why it fits so good. So whenever the value of p probability is high, then the fit is said to be good. It means that there is no significant difference in between the observed and expected value. And if the curve of the expected frequency is superimposed, then also we will say that there is not much divergence between the two expected and the observed frequencies, and fit would be good in the case. And in the last, if in the last section, whenever the value of p is small, whenever the value of p is small, then we say that fit is poor. That means there is a significant difference between the observed and the expected values. So this is the goodness of fit. Now let's talk about the steps of hypothesis testing, how we can perform the hypothesis testing. So in the first step, we'll calculate the value of chi-square. We had already seen the formula of chi-square. Then from the table, we read the value of chi-square for the given degree of freedom, that we will need the standard value of that chi-square. And then we'll find out the probability corresponding to the calculated values of chi-square. And if p is greater than 0.05, so this is, if p is greater than 0.05, that means if it is high, then we'll say that there is no significant difference and it is a good fit. And on the other case, if it is small, that is, it is lesser than 0.05, then we'll say that there is a deviation, there is a significant difference, and the good is it's not a good fit. So now let's see with the example how we can solve the problems. So let's talk about this question. The following table is given based on the data of fathers and sons light. Then we need to find out, test whether the color of the son's eye is associated with that of the father. So we have two different samples, and we'll have to see whether the both the samples are distinct or very much similar to each other. As being given the value of chi-square, the standard value of chi-square is given here. This is 3.84 for 1 degree of freedom. So now let's see the table. Now we need to calculate the frequencies. So how the frequencies are calculated, if you can see the table, just see the table. So this is the total of not light, this is total of light. So this is the total of basically this column, this is the total of this column. Here it is the total of this first row, this is the total of this second row, and obviously this is your grand total. So in every table we have to perform such type of calculations. We'll take the sum of the columns, we'll take the sum of the rows, and we'll calculate the grand total. So this is the GT. Now using these values we will be able to construct our frequencies. So for example, if you'll see in this first cell we have 378 cross 381 divided by 1000. So this is division is basically the grand total. This is the, for each cell we'll have to perform in the same way. This is the grand total, this is the sum of the row, and this is the sum of the column. So we've got the new value of the cell. Again, this is the grand total, this is the sum of the row, and this is the sum of the column. So we have got the new value. And similar way for the other cells also we'll perform the calculation. This is the grand total, sum of the row, and this is the sum of the column. So this is the grand total, sum of the row, sum of the column. So we have got these new values. Now we will use the formula of the chi-square. So we will calculate. So you can see this is the formula of the chi-square. Now for the first cell, 230 minus 144 divided by 144. So this is the observed frequency, this is the expected frequency, and this is the expected frequency. So we have these values. So this is the observed value and the expected value. So we can see what are the observed values and expected values. Let's see. So we have in the actual, the first cell, if we'll see in the first cell the actual value was 230. So this is 230, and the value we have calculated, this is 144. So we can use this formula that the observed value was 230, the expected value that we have calculated is 144. Similarly in the second cell, the observed value, and then the expected frequency, observed frequency, then these are the expected frequency, observed frequency, and these are the expected frequency. So we'll solve all these values, and then we finally will be able to calculate the chi-square. So in this case the chi-square is coming 133.37. Now let's find out the degree of freedom. If you remember, we had a talk of the formula of the degree of freedom, that is r minus 1 dot c minus 1. So we have two columns in this question and two rows. So the degree of freedom is 1, and for 1 degree of freedom the standard value has already been given into the question. So the standard value is given as 3.841. So now we see by comparing these values, we'll see that the calculated value is greater than the standard value, the chi-square. That leads to the conclusion that the hypothesis is wrong. So we have a wrong hypothesis, and the color of sun's eye is associated with that of father's to a great extent. That means there is a good similarity between the two samples, that is goodness of fitness. So both the samples fit each other, so there is no significant difference between the two samples, between the two data values. Now let's understand the another question based on the chi-square. Let's talk about this another question. It has been given from the following table showing the number of plants having some characteristics. Test the hypothesis that a flower's color is independent of fitness of leaf. So we have two rows and two columns into this. uh, this is the column, we'll sum these values in the column. This is the second column, we'll sum it up. Then this is the first row, we'll sum. Then this is the second row, we'll sum, and finally we'll calculate the grand total. So we will construct the table in the following manner, and once we construct the table in the following manner, we will construct and we will find the expected frequencies. So for each cell we'll calculate the expected frequency. Now if you'll see, so this is right, this is the grand total. As I have already told you to the last formula, this has to be the grand total, this has to be the sum of rows, and this has to be the sum of columns. Similarly, sum of rows, sum of column, grand total, sum of row, sum of column, grand total, sum of row, sum of column, grand total. So we will be able to calculate these expected frequencies for each cell. So these are the expected frequencies. Now we'll apply the chi-square, the formula. So in the formula, if again this is the observed, so this has to be 99. Please make a correction, this should be 99 here instead of 90, as we can see that this is given in the first cell 99. So we will take this as 99. So this is the observed, this is the uh, expected frequencies. You can see we have calculated the expected frequency. So now this is the observed and these are the expected, again observed and these are the expected, observed, expected, observed and expected. So in this way we will be able to calculate the value of chi-square. So you can see that the value of chi-square comes to be 0.2579. Now the degree of freedom, again with the same formula, r minus 1 c minus 1. In same case we have two columns and two rows, so the degree of freedom comes to be 1. By the standard value for the degree of freedom 1, that is 0.1 level of significance, the chi-square, the standard value of chi-square is 0.0158. Now just by comparing these two values, we can see that our calculated value, this is 0.2579, is greater than the standard value, that is 0.0518. So we'll see that this is greater than, obviously whenever the calculated value is greater than the standard value, then the hypothesis is always wrong, the hypothesis is rejected, and the flower color is independent of the flatness of the leaf. So we'll reject the hypothesis, and we can see that the flower color is independent of the flatness of leaves. So let's consider one more example in the same sequence for the chi-square test. The following table, the example number 88, the following table gives the number of aircraft accidents that occur in various days of the week. Find whether the accidents are uniformly distributed over or not, over the week or not. Uniform distribution, we'll have to check for the uniform distribution. So we have the table has been given where the days are given. You can see this is Sunday 14 accidents, Monday 16, Thursday 8, 12, 11, and lastly it's 14. So we need to calculate the chi-square. Before calculating the chi-square, we must be aware about the expected frequencies. So the expected frequencies, we have to take these expected frequencies. So it is been 12 in each day. So now just by using this formula, okay, how we have calculated this 12, let's discuss this. If we'll sum all these values, if we will sum all these values 14, 16, 8, 12, 11, 9 and 14, and will divide with the number of days, that is 1 2 3 4 5 6 7, so we have the value 12. Because it is a uniform distribution, if you will see in the question, that we have a uniform distribution. So we will keep the number of accidents same in all the days. So now this is 12. So I hope you have understood how this 12 came. We have added all the frequencies and divided it with the number of days, and we have distributed this throughout the week. Now we will calculate the chi-square with the observed value and expected values. Then for the second day observed value, these are the expected values. Third day observed value and the expected value. In the same manner, we will calculate the sum of all values, and we can see that the chi-square value coming here is 4.17. Now let's find out the degree of freedom. So now the degree of freedom is because we have only one row, that is in one column, so this will be the total number of observations minus 1. So this is 7 minus 1. So the degree of freedom comes to be 7 minus 1, which is equal to 6. Now the standard value of chi-square with degree of freedom 6 is 12.59. And now if we'll compare the two values, one is the calculated value 4.17 and this is the standard value 12.59. So we'll see that the calculated value is much lesser than the tabulated value. So this is the opposite case, and in this case we'll accept the null hypothesis. So on accepting the null hypothesis, we'll conclude that accidents are uniformly distributed over the week. So that's it for the lecture. Feel free to ask your queries and comment. Thank you so much.